smoke made the back mountain look hazy, but I put that photo on Photoshop anyways and play with contrast and color. There you go. It looks much more vibrant. It's magic of Photoshop. However, I still wish that I can do more with it. In Photoshop, you can maybe increase brightness and contrast, but you wouldn't be able to do bigger edits like changing time of day or changing the season. And let me tell you why these edits are not possible with Photoshop. It's because the output can only be generated using the pixels of the input image. If you want to add snow to this input image, you must have seen snow pixels from somewhere, and that somewhere is clearly not the input image. And this is exactly where machine learning can come into play. We can gain generic visual knowledge from a data set, and we can use that for creating new realistic visual that is nowhere present in the input image. So let's think about how to approach using machine learning for creating new images. Well, I'm sure most people will think about GANs. GANs work by randomly sampling a latent Z vector and transforming it to a realistic image. The realism is enforced by simultaneously training a discriminator that determines if the generated image looks realistic or not. One interesting thing about GANs is that they are like a random image generator. So if I want to edit my face, I should first find a corresponding latent vector that'll reproduce my photo. But it's not an easy thing to do. I can perform test time optimization in the latent space so that the output matches my photo, but it's too slow and imperfect. Here's another example of trying to reconstruct an outdoor scene. The two buildings, you can see that they're totally different. And for the purpose of image editing, there's really no reason that the output images should be generated from randomly drawn numbers. Instead, in my case, my generator for image editing will begin with the input image. Then from an external dataset, I hope to learn some way to blend in the pixels of the input image with the generic visual knowledge that's extracted from the dataset. Of course, this is not an easy thing to do. You train a neural network on the training set, and at test time, it should work well with the user-provided test image. So that's a typical machine learning problem, testing and training. And it's not only that, if you take too much from the data set, then you're ignoring the input image, and we're kind of back to this random image generation. On the other hand, you take too much from the input image, then you're not making meaningful edits to the image. So there is an inherent conflict between the input and the dataset. For this scenario, our model needs to disentangle the notion of snow from its geometry and apply to the structure of the input image. My works primarily focus on solving this conflict. So what's the most straightforward way to learn disentanglement? Well, we can have our model directly learn from the examples of input and output pairs created with human annotation. It's surely going to be expensive to prepare such a dataset, but we don't need to be so clever about figuring out the nature of disentanglement. So here's one useful application of this approach. In this setting, the input image contains layout of the scene along with the material type at each region. Then the output image should be a photorealistic image that follows the input layout. Clearly, the input layout does not contain any pixels that look photorealistic. Therefore, it must be learned from the dataset during training. So here's our method for training such a model. Given an input image from the training set and the output of our model, we compare it with the ground truth photo and optimize our model to match that photo. On top of that, we'll use the adversarial laws to enhance photorealism, and we train our model on a large dataset of such paired examples. Given a photograph, we use human annotation to draw the layout of each photo. Our model is trained to the inverse operation, going from layout to photo. So let's look at the results of such approach. There is an existing works named Pix2Pix and its follow-up Pix2Pix HD that uses this formulation. given these input layouts of the cityscapes dataset, we get these results. It produces quite realistic outputs. However, on more challenging dataset, we found that the results become quite bad compared to real photographs. The new dataset contains more than 150 labels instead of just 20 labels of the cityscapes dataset. It seemed mysterious that the outputs don't achieve photorealism at all, so I began debugging this. As the simplest case, I created some toy layouts where all pixels belong to the same sky class, and I pass it to the trained network of Pixelpix HD, and I get a gray image, which means I get zeros everywhere. Exactly the same thing happened with another tweet layout of grass label. I also get zeros everywhere. It looked like the model is ignoring the input and just outputting zeros. Why is this happening? After some investigation, I found that the issue was in the architecture. A standard deep network consists of convolutional layers followed by normalization layers, which works by making each layer output zero mean and unit variance. We know normalization yields nice properties for image recognition, such as smoother gradient flow or invariance to input scaling. However, normalization sometimes causes too much invariance if the input is uniform. It's because the output of convolution is also uniform, and after normalization, everything just becomes zero. In other words, the input signal is completely lost in the middle of the network. Therefore, I started the fix by providing the input over and over after every normalization layer of the generator network. By doing so, I could get the correct texture for the uniform layouts. Now let's take a closer look at how we provided the input signal. After normalization, we try to undo the harm by modulating the normalized activations by readjusting the mean and variance based on the input layout. The modulation is implemented with a few convolutional layers, and we named this module spatially adaptive denormalization, or SPADE in short. In the end, we could achieve much better realism than previous method. Using SPADE, we built a fun UI and presented it at SIGGRAPH. Basically, it looks like the Microsoft Paint app, but instead of the color palette, we provide a semantic palette of material types like ocean, sky, rock, and sand. Our app generates photorealistic images with the appearance of photographs but respecting the user-drawn layout. Lastly, note that there exist multiple plausible images that match the input. It would be nice if we can control the style of the output. To do this, we added some stochasticity to the network by starting with a random vector sampled from Gaussian, similar to standard GANs. And moreover, we additionally train an encoder network to capture the style of a reference image into the latent space. We also incorporated this feature into our UI. In the end, thanks to the paired supervision, our model achieves disentanglement of layout and appearance, along with the controllability of style, as well as high photorealism, like the reflection of the tree on the water. Now, let's take a step back and think about how useful this approach would be. Remember, training this model required preparing ground truth pairs. What if we want to transform horses to zebras? We can collect a bunch of horse photos and zebra photos, but we wouldn't be able to collect ground truth pairs with a horse and zebra posing exactly the same way. We can still throw in the GAN loss, but the discriminator will be happy as long as the output looks like any realistic zebra unrelated to the input. Therefore, in addition to the adversarial loss, we need another constraint. And to this end, we propose the cycle consistency constraint. We jointly train another image translation model in the reverse direction, and we enforce that the output zebra is back translated to the original horse. In more detail, given an input horse image, We first apply a forward mapping to translate into the zebra domain. Then we apply inverse mapping to reconstruct the input horse image. We simultaneously optimize these two networks to minimize the reconstruction error. This can help solving the correspondence problem because for the correct translation, the back translation has small cycle loss, while for incorrect translations, the cycle loss is going to be very large. And this is the result of our method, CycleGAN. One advantage about CycleGAN is that it's relatively easy to train the model because you just need to collect photos from two domains. We can also apply CycleGAN to style transfer applications. Like previous single image style transfer methods, we learn the style from all of the artist's paintings. We are also the first to do the opposite mapping, going from a painting to photo. CycleGAN can also be used for data augmentation for autonomous driving applications, like changing day to night. Here I translate individual frames independently so you can see the flickering. We can also turn real driving scenes into the style of computer graphics. Especially, CycleGAN can be used for domain adaptation. Let's say the goal is to train a semantic segmentation model. You can prepare a data set of RGB images and their segmentation maps. Then you get 93% accuracy in doing so. But the cost of human annotation will be very high. It may not generalize to rare scenarios. So you can reduce this cost by training your model in computer graphics, where the segmentation can be auto-generated. However, because of the domain gap, the accuracy drops considerably from 93 to 54. To reduce this domain gap, you can train a segmentation model on the stylized images to match the target dataset using CycleGAN. This approach improves the accuracy to 83%, which was the state of the art at the time of study. Moreover, domain adaptation is not the only application of CycleGAN. It can be used in many different applications, ranging from object editing, font transfer, data generation of license plates, or photo enhancement like image dehazing. It has also been used in other research fields like medical imaging, voice conversion, or even cracking simple ciphers. I think CycleGAN had an advantage of not requiring paired supervision with a loss function that can be generalized to other domains. However, it's not perfect. For one thing, 4 networks need to be trained, which makes it quite computationally heavy to use in conjunction with other models. Also, the cycle consistency loss is sometimes too constraining. And let me tell you in detail what this really means. Cycle loss is designed to promote sensible translation. By sensible, what I mean is that the translated zebra should retain some resemblance to the horse image. To achieve this, we trained an inverse translation function that's learned at the same time to minimize this pixel cycle loss. And of course, the back translation would be penalized if the pose of the translated zebra and back translated horse becomes too different. However, there are many plausible horses that correspond to the same zebra. Once the horse is transformed into a zebra, the color information of the horse is lost. Therefore, it shouldn't really matter which color the back-translated horse becomes. For example, a head should remain as a head, and feet should remain as feet as long as a head suddenly turns into a foot. And this is all we need. So let's directly implement this idea as a loss function. First of all, we use a GAN discriminator to make the output look like a zebra, but we need to make sure the structure is preserved. To do this, we consider a pair of input and output patch at the same location and enforce that the embeddings of the pair are similar. On the other hand, the patches from other locations should be mapped far from them. We formulate this as a contrastive loss. The corresponding input and output patches form a positive pair. Patches from other locations form negative pairs. In more detail, we use cosine similarities. We maximize the similarity of the positive pair while minimizing that of the negative pairs. And we do this by formulating a classification task with the target class as the positive pair. This formulation is called InfoNCE, was introduced and used in several works in representation learning. However, unlike MoCo and SimClear that used hand-designed data augmentation to produce positive pairs, we use the outputs of the generator that's learned at the same time. To project the patches into the embedding space, we use the first half of the generator as our encoder. Moreover, we found that computing the contrastive loss at multiple layers is important for stable training. In the end, our method replaces the fixed pixel-based cycle loss. And our method doesn't require a generator or discriminator in the inverse direction. As a result, our method can be trained faster than CycleGAN with a smaller memory footprint. This is going to be helpful when an image translation model is trained jointly with other models in a larger context, like domain adaptation or sim-to-real in robotics tasks. Also interestingly, we observed that the choice of negative patches is important. By default, we only sample the negatives from the same image, which we call internal patches. On the other hand, we can also include random patches from other images as additional negatives, which we call external patches. You know, in representation learning, it's known that a large number of external negatives improve performance. Instead, here we work at the patch level, so we can afford to use the same image as the source of our negatives. Indeed, when we tried to use external patches as negatives, the output quality was worse. We hypothesized that it's because the external patches are too easy to distinguish, and they sometimes even contain these false negatives like the highlighted horse hat patch. In fact, the power of internal patches has been well known in classic texture synthesis work, and more recently, training a super resolution network on the same but non-sampled image was shown to achieve competitive performance to other methods trained on the entire dataset. Likewise, our model fully leverages the internal statistics of a single input image. Here's a visual comparison of using internal versus external patches. Compared to default method, using the external patches causes more artifacts and signs of mode collapse. Also, we found that the samples from the target domain can be used for regularization following the identity loss used in CycleGAN. So normally we compute the contrastive loss using an image from the source domain, which is horse in this figure. But additionally, we can also provide a zebra image from the target domain as the input to the generator network. And we're still enforcing that the same contrastive loss to prevent making unnecessary changes to the input images. So in our final model named CUT, it's a short for contrastive unpaired translation, we use the identity regularization as well as the contrastive loss. As opposed to the pixel cycle loss, our loss is more flexible yet faster than CycleGAN. Actually, our method can be made even faster by not using the identity regularization, but using just a larger weight on the contrastive loss. So here we show the training speed of our method compared to CycleGAN. Note that we use the same network and GAN loss. The only difference is the contrastive versus pixel cycle loss. Also, when compared to other methods, our speed is much better than the two-sided methods and on par with one-sided methods. Here are the visual examples. It can be seen that CUT is able to make larger changes than CycleGAN, such as putting large zebra texture. Our method also performs well compared to more recent models. And lastly, fast CUT, due to larger contrastive loss, behaves more conservatively and hence more similar to CycleGAN. So What do I exactly mean by this more conservative transformation? Here's an interesting bias in the horse to zebra dataset that I have been playing with for 5 years. I use an off-the-shelf semantic segmentation network, and I found that the zebra pixels actually take up more than twice the horse pixels. That maybe I think it's just a bias of the photographer. When they're taking pictures of zebras, they want to emphasize the zebra stripe pattern. So I just figured that they maybe zoom in more than the horse photos. And if this is the reality, if this is the case, should the output zebras match the pixel frequency of the target or the source dataset? I think it's really a matter of personal taste, actually. In the more flexible cut model, we match the target zebra pixel frequency. If you carefully observe the highlighted portion, you observe that the cut model actually enlarges the horse body. In the more conservative fast-cut model, we better match the source, generating less zebra pixels. Still, both cut and fast-cut make more changes than CycleGAN, which could lead to more artifacts in the background in doing so. But after all, just like CycleGAN, our default cut model can be used on various image-to-image translation datasets. One way to quantitatively evaluate the quality of the results is using FID. It shows that our method is more powerful in distribution matching. We also measure the segmentation score on the cityscapes dataset. We first train an unpaired image translation model from layouts to photographs. Then we use a pre-trained segmentation network to predict the semantic class per each pixel. If the output images were realistic, the predicted segmentation should match the original layout. We measure how much the prediction agrees with the input, and the results show that cut can find ground truth correspondences better than existing methods. Lastly, since our contrastive loss only uses internal patches from the same single image, we can even apply our method on single image datasets. Here we take a high-res Monet's painting and translate it to the style of target photograph using the patch discriminator. And this setting connects image-to-image translation to image stylization method. So here's a famous painting by Monet. Using this reference photo, we first compare, we apply stylization methods to turn the painting into a photograph. But you see it's quite difficult. So here's the result of using Gaddis. Here's Strats. And here's a well-known photorealistic style transfer method called WCT by Jajun Yu, a postdoc at EPFL. It's not really designed to deal with non-photorealistic inputs, but well, here's a comparison anyways. And this is our results. We also tried a patch version of CycleGAN with pixel cycle consistency loss instead of the contrastive loss, but it produced more artifacts. And here's another result on Monet's water lilies. So let me summarize these works in the context of learning disentanglement. First, Spade was the easiest setting for learning disentanglement because the paired dataset directly suggested what the structure of the output should be. Next, we discussed the problem of unpaired translation, where we replaced the paired supervision with domain supervision. We introduced the cycle constraint to separate the style from the structure of the image. Now, let's take this one step further and discard the domain supervision as well. Within a collection of images, without any labels, can we still learn a meaningful disentanglement for image editing? This is my latest work presented at NeurIPS last year. If you have any questions about the works that I introduced so far, I'll be happy to answer them now. And another thing that I've discovered after publishing Cut is that if you actually enforce kind of bidirectional contrastive loss, what I mean is that right now the contrastive loss is between a horse and the generated zebra, right? So there's no place for the real zebra to come into play. So if you actually formulate another contrastive loss using real zebra patches some way, then I think it'll maybe have stronger representational
But I think
power
your
to
class
deal
model,
with
you
the.
also have this regularization term that you use the real
Mhm.
of the zebra.
Yeah,
Maybe,
so I think
maybe,
so the full formulation is, I think, maybe going to be more helpful.
yeah. Thank you so much. Do you have any more questions?
Hello.
Yes, please.
Yep.
I have one question regarding the CycleGAN you mentioned. So in CycleGAN, we know that there are some side effects, right? That the
Mhm.
model can hide information when it's translating from one to
Right.
another domain.
Mhm.
Did you see such artifacts, or did you see, for example, your model can handle better this type of artifacts or not?
So these artifacts are actually very imperceptible. So if I just rephrase your question, to reconstruct, to back translate the original input image, what the network does is it actually hides imperceptible, very small, high frequency pattern into the output image, so that this information is kind of hidden in the output image. And in many cases, these patterns are very small that the artifacts are not even observable that much. So we just think that it's actually magical that these very small patterns can contain so much information to reconstruct the input image. And yeah, these small patterns are imperceptible. And I thought maybe that's just good for generating realistic images.
Okay. So, okay, so you didn't basically see it impacting your work or, I don't know, making it
Mhm.
worse, for example.
Not much. One thing that I observe is so the results of translating zebras into horses. In that case, the zebra stripe pattern remains quite significantly. So maybe that's some artifacts, and it may be caused by cycle loss because the phase or the location of the zebra stripe pattern should remain in the output image. But at the same time, when I try just other formulations like maybe GAN without cycle loss, the generator also kind of struggle with consistently removing the zebra stripes. So I was suspecting that it may be not because of cycle loss, but it may be just because of the generator architecture that cannot handle removing the zebra stripes entirely.
Okay, but you, I think you still have these artifacts that, for example, even if like the shapes of the, let's say, horses and zebras
Mhm.
are different, the
Mhm.
model cycle consistency kind of forces it to be the same, right? Same for apples and oranges. You
Right,
still
right.
might have this artifact, right?
Yes.
Okay,
So that is kind of what we wanted, because we want to retain the structure of the input image. So if the structure of the input image is changed too much, then there's really no point of doing image translation. You might as well just generate random realistic images in the target domain. But one way to introduce more changes in the structure is simply just making your generator architecture downsample more. So the generator architecture of CycleGAN involves two steps of downsampling, and then do like residual blocks and then upsample twice. But if you just increase the number of downsampling and upsampling, the spatial resolution becomes smaller, so it's able to introduce more changes.
okay. Thanks. Yeah. Thank you.
Do we have more questions from this part? I think you can continue.
Yeah, so the direction is direction of my
Sorry, I
works
had
are.
one question.
Oh yeah, sure.
So it's just a small question. So for cut, you trained it over the cityscape segmentation maps as well, right?
Right.
And so like, how do you input the segmentation? Were they like, I'm sure they are not one hot encoded because then
Yeah, they are just RGB images. So it's a
okay.
stupid way that That's
Okay.
not really, yeah, it's just another data set that does domain image translation. So it's not really designed for things like
So,
segmentation.
okay, so I was wondering, like, if you have patches that are kind of homogeneous. For example, like in Cityscape, we only have 20 classes. So
Right.
there will be like at least 20 different, let's say, feature maps. Then you do you see if there's some problem when you try to do the contrastive loss of those like 20 fixed and trying to...
Yeah, that may actually, so in our setting, the input images were pretty small. So I think what it does is, because the boundaries are pretty close, it's actually possible to formulate contrastive loss in sensible way that does not collapse. But
Okay.
yeah, if there's like one large flat region, then I guess the best thing the contrastive loss can do is still map the same thing to the same embedding. So it's not as good as the case where the input is very diverse, but it's still the most optimal embedding
Okay.
to learn.
Yep. Thanks.
Yeah, so the most recent project that I did is removing as much as supervision as possible. So in Spade, we had paired supervision. And in case of CycleGAN or cut, we still had one label per each image. Like, does it belong to domain A or domain B? But what if we don't have any supervision? Then what can we do about it? So this is swapping autoencoder. And let's begin by contemplating what is the information that should remain unchanged after image translation. We talked about this in the previous slides. It's just basically that a head should still be a head. In other words, the structure is the representation that is invariant to changes in style across images. On the other hand, style can be viewed as the information that stays invariant within the image, like this zebra stripe pattern, but it should be distinct between images. So we can make this type of grid to visualize this. So our definition of this within image and cross image variation can be compared to maybe content and style definition used by Munit, Drit, Funit, and also StarGAN and image translation methods. The similarity is that the method also does something similar to content and style disentanglement, but the difference is that style is defined by domain label supervision in image translation works. So let's directly model this definition of style in our image manipulation model. Given an input image, we want to stylize that using a reference image to produce some output. How can we verify that the output captures the given style? Well, we can take random patches from the reference style image and test if an output patch looks indistinguishable. In this case, the output patch clearly stands out from the others, so the stylization was incorrect. But what about this case? In this case, the patches are indistinguishable, so we say the stylization was correct. So what I mean by style here, it maybe needs some clarification. Style, I think, is a quite general and overused term. Our way of defining style goes back a little bit of history and is motivated by the finding of Bela Illich, an experimental psychologist. He did many studies on how humans can distinguish texture. For example, in this image, you immediately see that there are two patterns. However, in this image, the distinction is not as clear, but magically, once we blur the pattern, you see that there exist two different patterns. I thought this was very cool. After these studies, he concludes that texture discrimination in human perception works by first extracting basic local features and then performing pairwise comparison of these features to tell if the patterns are the same. In other words, we should be able to set up a pairwise comparison test to see if the two patterns are the same texture. So let's do the test for ourselves. Let's take a data set of church images, and let's consider two random crops from this data set. Do they look like they are coming from the same image? Well, the answer is pretty easy. No, it's not too hard. What about these two? Yes, they are from the same image. And these two are from different images. But if we stylize this image, you see that it becomes much harder to answer. And we introduce a new adversarial training that exactly does this. So here's the full description of our method. First, our image manipulation model is modeled as an autoencoder, but unlike standard autoencoders, our encoder outputs two codes instead of one, representing structure and texture. And these two codes should have enough information to reconstruct the input image. And during training, we randomly sample another image, extract codes, and do code swapping to produce a hybrid image. Then we take a random crop from the hybrid image and compare it to the random crops of the input image. We train a patch-based co-occurrence discriminator that tells if the patches are all from the same image. In conclusion, our method learns this disentanglement of structure and texture. And note that these results may look similar to the style and content swapping grid of the StyleGAN paper, but it's different in that the input images are actually existing real images. Like you can recognize maybe a couple of churches in the input images. And this is the result on the Elson bedroom dataset. And you can see that the unique pattern of the style images are transferred. And because our method is an autoencoder, embedding input images is just one feed-forward pass of the encoder network. The reconstructed images are accurate because our structure code retains spatial resolution. Here are the results of standard GAN-based approaches. The reconstruction quality is worse, and they are also too slow for interactive image editing. Our quality of swapping is also better than existing methods. The standard GAN-based methods produce unrealistic images after embedding and swapping of real images. And the stylization methods also, they are not designed to handle this structure and texture swapping. But what's more interesting about our method is that the embedding space is smooth, allowing vector arithmetics. So if we collect 10 images of Summer Mountain on Google, we encode the images and average the codes, we get the code that represents summer mountains. We do the same thing on snowy mountains. And if we take the difference of the two vectors, we get a vector that'll add snow to other real input images. So these are user-provided input images like photo of Yosemite. Adding that vector as snow, subtracting that vector removes snow. If collecting 10 images is too much of a hassle, we can just run PCA on the codes of the training set, and it's similar to the idea of GAN space. We found that the first principal components are all meaningful edit vectors like adding snow, changing time of day, and so on. So our method can perform smooth interpolation of high-resolution images. It can also change things like weather condition, vegetation, season, color saturation, and many other things. Moreover, we built an interactive UI that lets you upload your own photos and begin editing. On the right side, you see previews of manipulating with the first 10 principal components in either positive or negative directions. And you can see that they are all kind of reasonable edits. Furthermore, now that we have disentanglement of structure and style, you can also separately edit the structure of the image while maintaining the style. For example, you can change the mountain ridgeline or change the river to make it a full circle. And these are the results of directly editing the structure code by simply cloning the code from other parts of the same image. Our method can also do domain translation if we just combine different domains as one large dataset. Using the UI, the user can control the specific style of the output, and this often results in superior quality. On faces, because the landmarks are aligned, we can run PCA on the flattened structure code to do spatial editing. And I said in the beginning that I like landscape photos, and I'm just very happy to see that my model can perform new types of image editing, and it's getting closer and closer to maybe producing realistic images that are actually useful. I also wanted to share my thoughts about the next project. It's still up in my head, so nothing has been really significantly done. But one limitation is that because our model is not required to learn about the underlying 3D structure of the scene, our model tends to make modifications to the structure. So you see here, the tree leaves are growing and shrinking. And that's because there's a correlation between astrophotos and the amount of sky. If it's a star photograph, photos tend to show more sky. I think photographers just tend to point upward. So our model actually captures that correlation as well. So it tries to reduce the size of ground. As a result, the underlying scene structure ends up changing. One way to prevent this would be to utilize some knowledge about 3D or physics. We can have our encoder also output some physics-based representation like 3D and enforce that the representation is consistent after some modification like viewpoint changes. Now the encoder is almost like a 3D computer vision problem. And on the other hand, the decoder is like a computer graphics pipeline. So it's not easy task. But there have been interesting feature representations that seem useful for my purpose. So here's HoloGAN and NERF. There have been a lot of follow-up works to NERF. And I think 2.5D representations like depth map or multi-plane imaging, I think for my purpose, we don't need perfect reconstruction of the scene. We're only interested in some intermediate representation that just looks plausible to human eyes or under some manipulation. In this sense, I think some variants of 2.5D representation is going to be nice. So thank you for listening to my talk. So we can have questions and answers for the last part of the presentation.
Thank you so much for the great presentation. So questions, please.
Can I ask a question?
Yes, please.
Could you please explain more about the structure code? Like, how do you ensure that one is about structure information and the other one is about texture information?
Yes, let me go back to the slides first. Yes. So there are two codes. The question is, they are intended to represent structure and texture, but how do you actually do that, right? So the definition for defining the texture is, I think, clear in terms of laws because we have this patch co-occurrence discriminator laws. And that formulation is maybe clear to understand because of the previous slides that I showed you. So if you cannot distinguish the patches, if they are from the same image or different images, we can assume that they have the same texture distribution. But the maybe one concerning thing is that we don't really define anything for the structure, right? So what may happen is maybe the model encoder is going to ignore the structure code entirely and then encode all the information in the texture code. Then in terms of loss formulation, it's fine. And yeah, it'll screw me up, right? It'll not do this disentanglement. And my way to solve this is relying on the strong inductive bias, or it's not even maybe bias. It's just encoded in the architecture of the encoder. And what happens is when I generate this texture code, I do a convolutional encoder, and then I get feature activations at each location, and then I just perform average pooling. And then it goes through a couple more NLP. But what happens is that I remove all spatial information. So the texture code by design cannot capture what things are at what location because I just did average pooling. And to make this even stronger bias, I also use reflection padding instead of zero padding in the initial convolutional encoder so that it's not able to measure its distance from the image border to encode in the locational information. And another very strong bias is that the structure code retains spatial resolution. So it's just a much, much better outlet to encode information that is specific to that location. And structure is what really makes one location different from other locations. Like if you think about face, right? Maybe I have the same style of face at all locations, but what makes my eye different from mouth is that it's just an internal thing, right? Like eye is different from mouth, and that's what makes this location different from another location, even in the same image. So in that regard, what I do is the receptive field of the structure code, each location of the structure code is not capturing the entire image. So just like it's kind of the other side of the definition of the texture code. It is only able to encode information that is specific for that location. And these inductive biases, we found that it's strong enough to encourage this disentanglement. We also tried with other formulations like structure code consistency loss. So what I do is we encode and reconstruct the input image, and then maybe we generate another image where the structure code is flipped, and that should correspond to actually flipping the image. So we also tried these versions, but it didn't really make noticeable improvement, but it comes at the cost of additional memory requirement. And our encoder decoder swapping model is already memory intensive. So this is like 2 encoders and 2 generators, and they are all StyleGAN2 architecture. So it's very memory intensive. So I just wanted to reduce all possible sources of unnecessary memory requirement.
Okay, thank you so much.
I have a question, please.
Mm-hmm.
So I think one of the important thing about is the patch size. So I think different patch size will give you different information, more global or more local. So
right.
Is there any kind of preference for the patch size choose?
Mm-hmm. So I found that it is actually surprisingly robust or not sensitive to the patch size. For all my experiments, I use patch size whose length of one side is like between 1/8 and 1/4 of the entire image. And that's the same setting I use for all datasets. Even if I increase the patch size to like 2/3 of the entire image, the results are a little bit different, but not too significantly different. Another thing that I just realized more recently is the number of patches we aggregate for the reference patch actually kind of impacts the role of patch discriminator more. So if I make, so in this figure, I'm making 4 random crops from the reference style texture image. But if I make only 1 crop, then patch discriminator just becomes weaker because it's harder to evaluate the distribution of the texture. So the texture code seems to play a smaller and smaller role. So it makes less structural changes in swapping. Yes, but it's actually quite robust to the size of each individual patches.
Okay, thanks. And I think maybe the reason because the objects, the objects you are trying to change is the main part of the image. So if there are multiple objects with different style, so I think maybe on that cases, patch size matters.
Oh, I see. So if you make the patch size bigger and it says that there needs to have 1 person, 1 building, and a car, then it should all appear. Yeah, maybe, yeah, maybe that's true. That's a good point.
Thanks.
Hello?
Yes, please.
Yep.
I have just one question regarding this. So here, if I understood correctly, you just apply two losses, right? One is reconstruction of the original image. The other one is the patch-based when you swap.
Well, there is another loss that I add to all image editing models, which is the GAN loss on the entire image. So it just acts as a way to bring up more realism to the output images.
Okay, on
So
the
they
output
are
of
actually,
G, basically.
yes, every output of G also is passed to the image discriminator.
Okay, and here you don't apply any contrastive loss, right?
No contrastive loss.
Okay, because something else you could do was that between the reconstructed image with the different texture and the original image, there is still some similarity of, let's say, the structure, right? You could exploit that, but in your case, you didn't need to do that, right?
Yeah, so almost like until like 1 month before submission, I actually had that in the formulation. So what we do is we re-encode the swap generated image or the reconstructed image and enforce that the structure code should be same as the structure code generated from the reference structure image. But it was kind of surprising that it didn't really change the results much. And I guess that's because the inductive bias that I already have in the architecture was strong enough. And it came at the cost of re-encoding the output images, and it's just more memory in the GPU. I don't have that many GPUs, so I try to save as much.
Okay. Yeah, that's interesting. Thanks.